Alright, welcome back to our unit on gases. Today's topic is Gay-Lussacs, combined and ideal gas laws. Lesson 3 of 3, your objectives are as follows. To understand the proportional relationship of Gay-Lussacs law. To understand how pressure, temperature, and volume are related using the combined gas law. And to understand the proportional relationship of Avogadro's gas law. And finally, to understand the behavior of an ideal gas in the equation PV equals nRT. Alright, for your quick write. In 1 to 2 sentences, answer one of the questions below. If you heat up a can of aerosol spray with a constant volume, how do you think it affects the pressure inside the can? Do you think the molecules move faster or slower inside the can? Okay. And if you have a balloon with 1 mole of helium atoms, 6.02 times 10 to the 23rd atoms or molecules, right? And you add another mole of helium atoms into that same balloon, okay, how do you think this affects the volume of your balloon? All right, so go ahead and pause this while you write and do your quick write. I'm going to move on. All right, so Gay-Lussac's law. Remember, according to the kinetic molecular theory, the average kinetic energy of gas particles is proportional to the temperature of the gas. In other words, more heat, right, equals faster molecules. So let's add some heat to our canister, okay, container here, and see how this affects the pressure through Gay-Lussac's law. Okay, so we're going to add some heat to see how it affects pressure. In other words, we're going to increase temperature to see how this affects the pressure. Okay, so we heat it up to 100 Kelvin. Notice, okay, our pressure gauge now reads 1 atmosphere, okay, and our molecules are moving faster. Okay, well, what do you think is going to happen if we heat it up even further? Okay, now we're adding even more heat to our atoms or molecules here. Notice they're moving faster, more collisions with the container, okay, and with each other, and now the pressure is reading 2 atmospheres. All right, and I think you get it by now. If we add even more temperature, all right, we increase it to 300 Kelvin. The molecules are moving extremely fast, and the pressure inside the canister is now 3 atmospheres, so the pressure has increased. Okay, more collisions mean more pressure. All right, and that's Gay-Lussac's law. He basically says that pressure and temperature are proportional. If temperature goes up, so does pressure, or vice versa. So, like I said, notice the addition of heat makes the molecules move faster. Faster molecules means more collisions, which means more pressure inside the container. This observation can be summarized by the following equation. Okay, P1 divided by T1 is equal to P2 divided by T2. Okay. So, for your notes, what is Gay-Lussac's law? Question on the left-hand side, answer on the right-hand side. Go ahead and pause this while you write. I'm going to move on. All right, the combined gas law. The laws of Boyle, Charles, and Gay-Lussac can be combined into one equation. This is called the combined gas law. Below is the combined gas law. It shows how pressure, volume, and temperature are all related. So notice we have to take into account 3 variables: pressure, volume, and temperature in the combined gas law. Okay? And when you're performing gas law calculations, remember the units must always match on both sides of the equation here. So for your notes, what is the combined gas law? Question on the left-hand side, answer, and please write down the equation on the right-hand side. Go ahead and pause this while you write. Okay, I'm going to move on. All right, so practice. Using the combined gas law that you just wrote down in your notes, try to see if you can solve this problem. A gas has a volume of 15.3 liters at 298 Kelvin and 2 atmospheres of pressure. What is the gas's volume at STP? Okay, standard temperature and pressure. So go ahead and pause this while you practice this. Go ahead and hit play when you're ready to check your work. All right, let's see how you did. So let's consider what we know, the initial conditions. The gas started at 15.3 liters in 2 atmospheres of pressure and a temperature of 298. Then we changed it to standard temperature and pressure, a pressure of 1 atmosphere, okay, a temperature of 273 Kelvin, and we're trying to solve for the gas's new volume. All right, so plugging in our values, we get 2 atmospheres of pressure, okay, 15.3 liters, and 298 Kelvin. All right, and then we changed it to STP conditions of 1 atmosphere and a temperature of 273 Kelvin. All right, and now we're solving for volume here. Okay, remember. So what I recommend is simplifying the left-hand side of the expression here. Okay, and we get 0.10 is equal to 1 atmosphere multiplied by V2 divided by 273 Kelvin. So now we just simply need to multiply this side by 273 Kelvin and we can solve for V2. And we get, okay, 27.3 liters for V2. So the volume, okay, has increased. All right, hopefully you got that right. Okay, so Avogadro's law. Now we're not looking at really anything except for volume and the amount of gas molecules or moles of gas. Okay, so let's say we have 1 mole of gas here and with a volume of 200 milliliters. All right, and our graph shows this. Okay, 1 mole of gas which has a volume of 200 milliliters. Okay, now let's add 1 more mole of gas in here and see what happens. Well, okay, 1 mole of gas added gives us 2 total moles of gas. Notice the volume has increased, so the volume of the gas has gone up. Okay, so by adding more gas molecules or atoms, volume increases. Well, what do you think is going to happen if we were to add 1 more mole of gas? How do you think this will affect volume? Well, in other words, let me rephrase that. What would happen if you just simply blow more air into a balloon? How would that affect its volume? Okay, well, think about it. We're going to add 1 more mole of gas. Okay, now we have 3 moles of gas total. And notice, okay, as more moles or molecules of gas are added, the volume of the container increases. Okay, so in other words, as we just add more molecules or atoms of gas, the volume of the container gets bigger. Okay, it's just like blowing air into a balloon. As you blow more molecules or atoms into the balloon gets bigger, right? Pretty basic law. And well, that's pretty much Avogadro's law. Okay, so for your notes, what is Avogadro's law? Okay, question on the left-hand side, answer on the right-hand side. Go ahead and pause this while you write. I'm going to move on. Ideal gas law. The ideal gas law explains the behavior of an ideal gas. Most gases obey this equation or law when at ideal conditions. Ideal conditions are at STP, 1 atmosphere pressure and 273 Kelvin. In other words, most gases behave the same way at 1 atmosphere pressure and 273 Kelvin. Okay, where PV equals nRT. Okay, so P, as you might have guessed, represents pressure. V represents volume. N in this case is the number of moles of a gas. Okay, and R is a constant. And T, as you might have guessed, represents temperature. Okay. So an ideal gas is a hypothetical gas that exactly obeys the ideal gas law. Okay, PV equals nRT. R is a constant and is always equal to 0.0821 liters multiplied by atmospheres divided by kelvins per mole. Okay, which means, all right, because our constant uses liters, atmospheres, kelvins, and moles, our pressure, volume, and temperature measurements must be in those units as well. So when working with the ideal gas law, like I just said, very important, units must be in liters and atmospheres and kelvins. Okay? So for your notes, what is an ideal gas? Question on the left-hand side, answer on the right-hand side. Go ahead and pause this while you write. I'm going to move on. Okay, so now that you have the ideal gas law written down, go ahead and practice and see if you can solve this question. So go ahead and pause this. When you're ready to check your work, hit play. Okay, let's see how you did. If you have 4 moles of a gas at a pressure of 6 atmospheres and a volume of 12 liters, what is the temperature of the gas? Okay, it's basically like a lot of the problems we've done in the past where you can plug in your values here. All right, so let's think about what we know here. Okay, we know pressure, we know our volume, we know the moles or the quantity of the gas. Okay, we know R is a constant. Okay, and we're solving for the temperature. All right, so let's rearrange our ideal gas law for T. Okay, we get the following equation. All right, notice I just brought over my N and R and I divided it by my pressure and volume here. Okay, now we can substitute in our values. 6 atmospheres of pressure. All right, a volume of 12 liters. All right, now we have our mole values, 4 moles. And our R, our constant, 0.0821. Okay, and solving for T, we get 219.2 Kelvin. That is the temperature of our gas. All right, hopefully you got that right. Okay, so go ahead and summarize. Remember, you can always write your own. Okay, so go ahead and complete your summary for 20 easy points, and we'll see you next time.